myself Impala MG, studying in Sri Venkateshwara College of Engineering. Today my topic is additional list operators, spare matrix, double linked list. Additional list operations. Operations for chains. Operations for chains is often necessary and desirable to build a variety of functions for manipulating single listed lists. Some that we have are getNode and retNode, which get and return nodes to the available space list. Here is a program for operation. Linked list operations transfer, insert, and delete. Transversal means access each element of the linked list. Insertion, it adds a new element to the linked list. Deletion, it removes the existing elements. Search, find a node in a linked list. Sort, it sort the nodes of the linked list. Insert elements to a linked list. Insert at the beginning. Allocate memory for new node. Store data. Change next of new node to point to head. Change head to point to recently created node. Here is the program for insert at the beginning. Insert at the end. Allocate memory for new node. Store data. Transfer to last node. Change next of last node to recently created node. Here is the program for the insert at the end. Insert at the middle. Allocate memory and store data for new node. Transfer to node just before the required position of new node. Change next pointers to include new node in between. Here is the program for the insert at the middle. Concatenating single linked list. Concatenating list combines two or more lists into a single list. It is done using the plus operator. The order of list determines the order of elements in the final concatenated list. Concatenating or joining two linked lists is not at all a difficult task. We just need to follow some very simple steps. And the steps to join two simple lists are transfers over the linked list A until the element next to the node is not null. If the element next to the current element is null, A is lesser than next null. Then change the element next to it to be B. B is equals to B. Operations for circularly linked list. Operations for circularly linked list like the one by keeping a pointer last to the last node in the list rather than to the first. We are able to insert an element at both the front and end with ease. Had we have kept a pointer to the first node instead of the last node, inserting at the first would require us to must move down the entire length of the list until we find the last node so that we can change the pointer in the last node to point the new first node. Extending list. Extending list adds elements from another iterable to the end of an existing list. It is done using the extend method. The original list is modified in place. This is the representation of extending list. Sparse matrix. Sparse matrix representation. In a sparse matrix representation, we only store the non-zero elements of the matrix to save memory space. One common way to represent a sparse matrix is by using a linked list data structure. Each element of the linked list represents a non-zero element in the matrix. The node structure typically contains three fields: row, column, and value. The row and the column fields stores the indices of the non-zero elements, and the value field stores the actual value of that element. To represent the space matrix, we create a linked list of nodes where each node represents a non-zero element. The head of the linked list points to the first node, and each node's next points to the pointer to the next node in the list. By using this representation, we can efficiently store, access the non-zero elements of the matrix without wasting memory on the zero elements. Representation of spare matrix. One common representation is the compressed spares row CSR format, which stores the matrix values, row indices, and column pointers. Another representation is the compressed spares column CSC format, which is similar to CSR but stores the column indices instead of the row indices. Many libraries and software packages provide efficient implementation of spare matrix representation. This is the representation of spare matrix. Spare matrix operations. Addition and subtraction of spare matrix can be performed by adding or subtracting corresponding non-zero elements. Multiplication of spare matrix can be done using various algorithms such as the CSR or CSC format. Spare matrix can be transformed through operations such as transformation and scaling. Spare matrix additions representation is given below. Erasing a spare matrix. The function measures implements the erase operation. Here is an example for erase a spare matrix. Row columns is equals to 1000, which deletes the row 573. The row of 553 gets deleted. Double linked list. Double linked lists are the type of data structure where each node contains a reference to the previous node and the next node in the list. This allows for efficient transversal in both directions. In a double linked list, each node has two pointers, one pointing to the previous node and one pointing to the next node. This allows us to easily move forward and backward through the list. A node in a double linked has at least three fields: a left link, a data field, and a right link. The necessary declaration are memory representation of double linked list. Memory representation of double linked list is generally double linked list consumes more space for every node and therefore causes more expansive basic operation such as insertion and deletion. However, we can easily manipulate the elements of the list since the list maintains pointers in both the direction, forward and backward. The first element of the list, that is 13, stored at address 1. The head pointer points to the starting address since this is first element being added to the list. Therefore, the preview of the list contains null. The list node of the list resides at address 4. Therefore, the first node contains 4 in its next pointer. Advantages of double linked list. Double linking allows transversal in both directions, making it efficient for operation such as reverse transversal or deletion of a node. Insertion and deletion of nodes can be done in constant time if the position is known. Double linked lists can be used to implement other data structures like stacks, queues, and associative arrays. The representation of double linked list is given below. Reversing the double linked list is very easy. It can allocate or reallocate memory easily during its execution. As with a single linked list, it is the easiest data structure to implement. The transversal of this double linked list is bidirectional, which is not possible in a single linked list. Disadvantages of double linked list. Extra memory is required to store the pointers for each node, making double linked list slightly more memory consuming than single linked list. Operations like insertion and deletion require updating multiply pointers, making them more complex than in single linked list. Double linked lists are not suitable for the application where memory is a constraint. It requires more memory to store the extra points. It is more complex implementation than single linked list. They require extra operations to maintain the integrity of the list. It is slower transversal than arrays for random access. Compared to a single linked list, each node stores an extra pointer which consumes extra memory. Operations require more time due to overhead of handling extra pointers as compared to single linked list. No random access to elements.